Have a nice time to learn finite element method. Many problems in engineering and applied science are governed by differential or integral equations. The solution to this equation would provide an exact closed form solutions to the particular problem being studied. However, the complexities in the geometry, properties and in the boundary conditions that are seen in most real-world problems usually means that an exact solution cannot be obtained or obtained in a reasonable amount of time. Current product design cycle times imply that engineers must obtain design solutions in a short amount of time. They are content to obtain approximate solutions that can be readily obtained in a reasonable time frame and with reasonable effort. The firm is one such approximate solution technique. The firm is a numerical procedure for obtaining approximate solutions to many of the problems encountered in engineering analysis. In the FEM, a complex region defined a continuum is discretized into simple geometric shapes called elements. The properties and governing relationships are assumed over these elements and expressed mathematically in terms of unknown values at specific points in the elements called nodes. An assembly process is used to link the individual elements to the given system. When the effects of loads and boundary conditions are considered, a set of linear or nonlinear algebraic equations is usually obtained. Solution of these equations gives the approximate behavior of the continuum or system. The continuum has an infinite number of degrees of freedom, while the discretized model has a finite number of degrees of freedom. This is the origin of the name finite element method. The number of equations is usually rather large for most real-world applications of FEM and requires the computational power of the digital computer. The FEM has little practical value if the digital computer were not available. Advances in and a ready availability of computers and software has brought to the FEM within the reach of engineers working in small industries and even students too. Two features of finite element method are worth nothing. The piecewise approximation of physical field on finite elements provides good precision even with simple approximating functions. Simply increasing the number of elements can achieve increasing precision. The locality of the approximation leads to space equations for a discretized problem. This helps to ease the solution of problems having very large number of nodal unknowns. It is not uncommon today to solve a system containing a million or primary unknowns. Origin of the finite element method. It is difficult to document exact origin of FEM because the basic concepts have evolved over a period of 150 more years. The term finite element was first coined by Clough in 1960. In the early 1960s, engineers used the method for approximate solutions of problems in stress analysis, fluid flow, heat transfer, and other areas. The first book on FEM is Chinkia Vyas and Chung was published in 1967. In the later 1960 and the early 1970, the term was applied to a wide variety of engineering problems. The 1970 marked advances in mathematical treatments, including development of new elements and convergence studies. The most commercial FEM software package originated in the 1970s Abacus, Arduino, ANSYS, Mark Zwick, 1986 Fenris Lastron, 80C SAM 80. FEM is one of the most important development in computational method to occur in the 20th century. In just a few decades, the method has evolved from one application in structural engineering to widely utilized and richly varied computational approach for many scientific and technological areas. FEM helps the design engineer. The FEM offers many important advantages to design engineers, easily applicable to complex, irregular shaped objects composed of several different materials and having complex boundary conditions. Applicable to steady state, time dependent, and eigenvalue problems. Applicable to linear and nonlinear problems. One method can solve a wide variety of problems, including problems in solid mechanics, fluid mechanics, chemical reactions, electromagnetics, biomechanics, heat transfer, and acoustics to the name new. General purpose FEM software package are available at reasonable cost, can be readily executed on microcomputers including workstations and PCs. The FEM can be coupled to CAD programs to facilitate some modeling and mesh generations. Many FEM software packages features GUI interface, auto measures, and sophisticated post-processor and graphics to speed the analysis and make pre- and post-processing more user-friendly. Simulation using FEM also offers important business and advantages to the design organization. Reduced testing and redesign costs, thereby shortening the product development time. Identify issues in designs before tooling is committed. Refine components before dependencies to other computer. Prohibit changes. Optimize performance before prototyping. Discover design problems before litigations. Allow more time for designer to use engineering judgment and less time turning the crank. Theoretical base. Several approaches can be used to transform the physical formulation of problem to its finite element, discrete analog. If the physical problem is described as a different equation, then the most popular solution method is method of weight residuals. If the physical problem can be formulated as minimization functional, then variational formulation is used. One family of methods used to numerically solve differential equations are called methods of weight residual. Method of weight residual, an approximate solution is substituted into the differential equation. Since the approximate solution does not identically satisfy the equation, a residual or error term results. Consider a differential equation dy double dash of x plus q is equal to 0. Suppose y is equal to h of x is an approximate solution to 1. Approximate substitution then given dh of x plus q is equal to r is non-zero residual. Method of weight residual then requires that s w of x r into x is equal to 0, where wx is the weight function. The number of weight functions equals the number of unknown coefficients in the approximate solution. Theoretical basis Galerkin method. There are several choices for weight residual weighting function W. In the Galerkin method, the weighing functions are the same functions that were used in the approximating equations. The Galerkin method yields some results as the variational method when applied to different equations that are self-adjacent. Method of weight residual is therefore an integral solution method. Many readers may find it unusual to see a numerical solution that is based on integral formulations. The variation method involves the integral function of the product member. Each new function produces a new number. Function that produces the lowest number has the additional property of satisfying specific differential equation. Consider p is equal to d by 2 y double dash of x minus q of y into dx is equal to 0. The numerical value of p can be calculated given specific equation y is equal to f of x. Variation calculation shows that particular equation y is equal to g of x, which yields the lowest numerical value for p, is the solution to the differential equation.